Good morning to all. Today we'll discuss the problems on the right hand limit and left hand limit. We know that if right hand limit and left hand limits are equal, then the function limit of f of x does not exist. If right hand limit and left hand limit are not equal, then function does not exist. If equal, then function exists. So on the concept of this, now we'll see some problems. Example, show that limit of a function f of x, as x tends to 0, does not exist, if f of x is equal to mod x upon x, and x is not equal to 0, and f of x is equal to 0 at x is equal to 0. Now we see the solution. Mod x is equal to x for x is greater than or is equal to 0, and mod x is equal to minus x for x is strictly less than 0. Now this implies that therefore limit of a function f of x, right hand limit of a function f of x as x tends to 0 plus, so this is a right hand limit of a function f of x as x tends to 0 असंही म्हणलं तरी चालेल, किंवा limit of a function f of x as x tends to 0 plus असं म्हटलं तरी चालते. This is equal to limit of a function f of 0 plus h as h tends to 0, This is equal to limit of a function 0 plus h divided by 0 plus h as h tends to 0, limit of a function mod 0 plus h divided by 0 plus h, and this can be written as limit as h tends to 0 of a function mod h divided by h, and this can be written as limit of a function h upon h as h tends to 0 is equal to limit as h tends to 0 of a function 1 is equal to 1. This is a right hand limit. Now what is for left hand limit? Similarly, for left hand limit of a function f of x as x tends to 0 minus, as x tends to 0 minus, this can be written as limit of a function f of 0 minus h as h tends to 0, and therefore this is equal to limit of a function mod 0 minus h divided by 0 minus h as h tends to 0. Again this is equal to limit as h tends to 0 of a function mod minus h upon h is equal to limit as h tends to 0 of a function minus h upon h. Again this is equal to limit of a function as h tends to 0 minus h upon h is minus 1. So this is equal to minus 1. So this right hand limit and this left hand limit are not equal, and if they are not equal, so limit of a function f of x as x tends to 0 does not exist. If they are not equal, limit of a function f of x as x tends to 0 does not exist. So we write here this limit of a function f of x as x tends to 0 plus, this is right hand limit, is not is equal to this left hand limit of a function f of x as x tends to 0 minus. So, and therefore limit of a function f of x as x tends to 0 does not exist. Does not exist. Now we'll see the another problem, another more problem. Another problem is, these problems are very easy. If you practice it, you will get more interest in this mathematics subject. Now another problem. Let f of x is equal to x is equal to greatest positive integer greatest positive integer not greater than x, not greater than x. Find limit of a function f of x as x tends to 2 plus 0, that is a right hand limit of a function f of x as x tends to 2. Then left hand limit of a function f of x as x tends to minus 2. X tends to 2 minus 0. And the function and a function f of x and a function limit of function f of x as x tends to 0. We want to find this. Now we'll see the solution of this example. Limit. We have let. We have given this f of x is given f of x is equal to greatest positive integer not greater than x. So we have limit of a function f of x as x tends to 2 plus 0. That means right hand limit of the function f of x as x tends to 2 is equal to limit of a function f of x. X is 2 plus h as h tends to 0. This can be written in this way. This can be written in this way. Again, this is equal to limit as h tends to 0 of a function 2 plus h is equal to limit as h tends to 0 is 1 here. So h tends to 0 here is 0. H tends to 0 is 0. So what we get? Here we get 2, not 1. So, and this is equal to 2. This is a right hand limit of a function f of x as x tends to 2. Similarly, for left hand limit of a function f of x as x tends to minus 0. This can be written as limit as h tends to 0 of a function f of 2 minus h. Bracket close. So this is equal to, again, limit as h tends to 0 of a function 2 minus h, and therefore this is equal to limit as h tends to 0 is equal to 2. H tends to 0, this will be 0. What we get? This is 2. So this implies that limit of a function f of x as x tends to 2 exists, and therefore limit of a function as x tends to 2, this is left hand limit of a function f of x is equal to limit of a function f of x that is right hand limit of a function f of x as x tends to 2 plus. So we also solve this problem. Now we'll see the next problem. Another example is let f of x is equal to 2 cos x where this x is greater than or equal to 0 and f of x is equal to 3x plus m where x is strictly less than 0. Find the value of the constant find the value of the constant m if limit of a function f of x as x tends to 0 exists. Now you see the solution of this problem. Solution. We have given that the function f of x is equal to 2 cos x if x is greater than or equal to 0 and f of x is equal to 3x plus m if x is strictly less than 0. We have given. So let limit of a function f of x as x tends to 0 exists. Then what do we have? Then right hand limit and left hand limits are equal. So then we have limit of a function f of x as x tends to 0 minus, that means this is left hand limit, is equal to right hand limit of a function f of x as x tends to 0 plus. So what do we have? Therefore, limit as h tends to 0 of a function f of 0 minus h is equal to limit of a function f of 0 plus h as h tends to 0. Therefore, limit as h tends to 0 of a function, we have 3x plus m, but x is 0 minus h, f of x is 0 minus h. So in place of this x, we write 0 minus h. So limit of function f of x, that is 3, and x is a 0 minus h plus m as it is, So this is equal to limit. Now we will take this limit as h tends to 0 of a function 3 f of x is 0 plus h here, and plus m as it is, So this is for this, but for this we have not this. Limit as h tends to 0 f of 0 minus h. So function is 3 as it is, for x that is 0 minus h plus m as it is. So now for this, limit as h tends to 0 to cos of 0 plus h. Cos x is f of x is cos x is 0 plus h here. So what we get? Therefore we get limit as h tends to 0, this will be minus 3h plus m, which is equal to limit as h tends to 0 to cos h. So as h tends to 0, this will be 0, and what we get? We get this is a 0 plus m, and this is equal to 2 cos h, cos 0, in place of h there will be 0 because of limit h tends to 0. So cos 0 is 1, 1 into 2 is 2. So what we get? We get m is equal to 2. Now we have find the values of constant m. Now let's see the next example. Next example is if f of x is equal to mod x minus 2 divided by x minus 2 and f of x is equal to 1. F of x is equal to mod x minus 2 divided by x minus 2 if x is not is equal to 2, and f of x is equal to 1 if x is equal to 2. Now find the right hand limit, left hand limit, and the limit of a function f of x as x tends to 2. So find limit as x tends to 2 plus, this is the right hand limit of a function f of x. Then limit as x tends to 2 minus, this is the left hand limit of a function f of x, and limit as x tends to 2 of a function f of x. We want to find this. So we'll see the solution. We have given this function f of x is equal to mod x minus 2 upon x minus 2 if x is not equal to 2, and the function f of x is equal to 1 if x is equal to 2. Now we have right hand limit of a function f of x as x tends to 2 plus or to positive. This can be written as limit of as h tends to 0 of a function f of 2 plus h, f of 2 plus h. So this is equal to limit as h tends to 0 f of 2 plus h, f of x. In place of x there is a 2 plus h, so mod in place of x we write 2 plus h minus 2 divided by x is 2 plus h minus 2. So what do you get? You get this is equal to this 2 will be cancelled. So limit as h tends to 0 of a function mod h upon h. So this is equal to limit as h tends to 0 of h upon h is equal to limit as h tends to 0 is 1, and therefore this is equal to 1. This is the right hand limit. Now for left hand limit of a function f of x as x tends to 2 minus, that is left hand limit of this function. What you get? You get limit as h tends to 0 of a function f of 2 minus h. So what you get? In place of x we have 2 minus h, so this is equal to limit as h tends to 0 of a function mod x is 2 minus h minus 2 divided by x is 2 minus h minus 2. What do you get? You get this is equal to limit as h tends to 0, 2 will be cancelled, mod minus h divided by minus h. So again this is equal to limit of a function mod minus h is h divided by minus h as it is. Mod of minus h is equal to h, so this we write here h, and minus h as it is, and limit as h tends to 0. So what do you get? You get this limit as h tends to 0 of a function, h will be cancelled, here will be minus 1, and this will be is equal to minus 1. So right hand limit, this right hand limit and this left hand limit, it does not exist because of these are not equal. So therefore limit of a function f of x as x tends to 2 plus is not is equal to limit of a function f of x as x tends to 2 minus. These are not equal, and therefore limit of a function f of x as x tends to 2 does not exist. Does not exist. Now again we'll see the another problem. For the why I am taking these problems, because your concept of limit, that is right hand limit and left hand limit, must be clear. So I am taking the more examples for your understanding, or for to fit the concept in your head, or you and also for your best understanding of the limits chapter. When we solve so many problems, then concepts will be more clear and clear. It becomes more clear and clear. So now we'll see another example also. Prove that limit of a function sin x as x tends to a is equal to sin a, and find delta in terms of epsilon. Now we see the solution. We know that sin x is defined for all real x. Also we have mod of sin x is strictly less than x, and mod of cos x is less than or is equal to 1 for all. This sign is for all belongs to R. Here R is the set of real numbers which is lie on the real line. Now let epsilon is greater than 0. Let epsilon is greater than 0 be given. Let epsilon be greater than 0 be given, and therefore mod of sin x minus sin a can be written as, mod of 2 sin x minus a divided by 2 into cos of x plus a divided by 2, and this is equal to, this can be written as 2 mod of sin x minus a divided by 2 mod cos of x plus a divided by 2, which is strictly less than 2 mod of x minus a divided by 2 into 1 and this is equal to 2 will be cancelled. What do we get? We get mod x minus e, because we know that mod of sin x is less than x and mod of cos x is less than or is equal to 1. So we can write this 2 mod of x minus a upon 2 will be cancelled and we get mod x. This is equal to mod x minus e. So we choose delta is greater than 0. We choose delta is greater than 0 such that delta is equal to epsilon, and therefore this 0 is less than mod x minus a, and mod x minus e is less than delta, and therefore this implies that mod of sin x minus sin a is strictly less than epsilon. Because of delta is equal to epsilon. So this delta is equal to epsilon, and mod x minus a is a mod of sin x minus sin a. So we write this mod of sin x minus sin a is strictly less than epsilon. So this implies that therefore limit of a function sin x as x tends to a is equal to sin a. We have proved this. Now we see all these problems. Now we will see what are the theorems on limit. So we will discuss some theorems on the limit. Now we will see some theorems on limit. Theorems on limits. Now see the theorem first. Statement. What is the statement of theorem first? Statement of theorem first is if limit of a function f of x as x tends to x0 exists, then it is unique. This is the statement of theorem first. Now we see the proof of this theorem. if possible, let there be two limits L1 and L2 with the two limits. Let possible there will be L1 and L2 be two limits. Then what do you have? Then limit of a function f of x, as x tends to x0 is equal to L1 implies that for any epsilon is greater than 0, there is a delta 1. There is a delta 1 which is greater than 0, such that 0 is strictly less than mod x minus x0, and mod x minus x0 is strictly less than delta 1, and this implies that mod f of x minus L1 is strictly less than epsilon by 2. This is strictly less than epsilon by 2. Suppose this is number 1. Now, and another limit L2. So, and limit of a function f of x as x tends to x0 is equal to L2. This implies that for any epsilon is greater than 0, there is a delta 2 is strictly greater than 0, such that 0 is less than mod x minus x0 is strictly less than delta 2. So in place of here L1, they write L2, you get same, and in place of delta 1 there is delta 2. So this implies that mod of f of x minus L2 is strictly less than epsilon by 2. Suppose this is equation second. Now, if delta is equal to minimum of delta 1 delta 2, then this first and second gives, or from the first and second, if delta is equal to minimum of delta 1 delta 2, then we get from first and second, what we get? We get from this 0 is strictly less than mod x minus x0 and is strictly less than, in place of delta 1 delta 2 there will be right delta. From these two we get this. So this implies that the same thing, that is the mod f of x minus L1, mod f of x minus L1 is strictly less than epsilon by 2, is strictly less than epsilon by 2, and mod f of x minus L2 is also strictly less than epsilon by 2, is also strictly less than epsilon by 2. Suppose this is 3. Suppose this is 3. Now what we have? Mod L1 minus L2, mod L1 minus L2 is equal to mod L1 minus f of x. Mod L1 minus L2 can be written in this form. That is, we add f of x and subtract f of x, or we subtract f of x or add f of x in this mod. So L1 minus f of x, we have subtract f of x, add f of x, and then minus L2 as it is, minus L2 as it is. This mod L1 minus L2 we can write in this form, and that is, this is less than or is equal to, what we get? We get L1 minus f of x plus mod f of x minus L2, mod f of x minus L2. So this implies that mod L1 minus L2, this mod L1 minus L2 is strictly less than, what is L1 minus F1? L1 minus f of x in the mod L1 minus f of x is epsilon by 2, or f of x minus L1 is also epsilon by 2. So this is the same. In the mod minus x is equal to x. So this is epsilon by 2, and plus f of x minus L2 is also epsilon by 2. So we write here epsilon by 2 for 0 is strictly less than mod x minus x0, which is strictly less than delta, by this equation. Sorry, we have 0 is less than x minus, mod x minus x0 is less than delta. For this, by using this 3 we get this. So therefore what we get? Therefore we get mod L1 minus L2. L1 minus L2 is strictly less than, what is addition of 2 epsilon upon 2? So 2 will be cancelled and we get epsilon for any positive epsilon. For any positive epsilon. For any positive epsilon, and therefore what you get? Therefore you get L1 minus L2 is equal to 0, and that is L1 is equal to L2, means these are the unique. Hence the limit if exist is unique. Hence the limit exists is unique. We have proved this theorem first. Now we'll see the theorem second. Now we see the statement of theorem second. Statement of theorem second. If limit of a function f of x as x tends to x0 is equal to L, then f is bounded, on some deleted neighborhood of deleted neighborhood of x0. Statement of the theorem second is, if limit of a function f of x as x tends to x0 is equal to L, then f is bounded on some deleted neighborhood of x0. We want to show f is bounded on some deleted neighborhood of x0. So we have already seen the definition of deleted neighborhood, delta. So by using that definition, we will see this proof of the theorem second. Suppose that limit of a function f of x as x tends to x0 is equal to L, then by definition for any epsilon is greater than 0, there exists a delta is greater than 0, there exists a delta is greater than 0 such that such that 0 is strictly less than mod x minus x0, which is strictly less than delta, and this implies that mod f of x minus L is strictly less than epsilon. This implies, we know that this. So now therefore mod f of x is equal to mod of f of x minus L plus L is less than or is equal to, this can be written as mod f of x minus L plus mod L, and this is strictly less than epsilon. We know that mod f of x minus L is strictly less than epsilon. So this is epsilon plus mod L as it is. Mod L as it is for all x such that this 0 is strictly less than mod x minus x0, and mod x minus x0 is strictly less than delta. And therefore this implies that f of x is a bounded on a bounded on a deleted neighborhood of x0. We have seen these two theorems. Now tomorrow we will see the remaining theorems on the limit. Today we will stop here. Thank you to all. You attend these lectures regularly, because if you attend these lectures regularly, you understand the next problems, next theorems of this integral and differential calculus. So in the exam of you must do the study regularly. Okay, today we stop here. Okay, thank you.